Hello students, in this video we discuss about Cayley-Hamilton theorem. Actually, Cayley-Hamilton theorem is based on a characteristic equation. Cayley-Hamilton theorem states that every non-singular square matrix satisfies its own characteristic equation. So suppose we have a square matrix A which is non-singular. Non-singular means its determinant is non-zero and its inverse exists. If a matrix is non-singular, then its inverse will definitely exist. So every non-singular square matrix satisfy its own characteristic equation, and characteristic equation is what? Suppose A is square matrix, then determinant of A minus lambda is equals to 0 is known as characteristic equation, where lambda is some scalar value. So about that scalar value we can find characteristic polynomial, and when which is determinant A minus lambda is equals to 0, it becomes an equation, and the roots of that equation, that is for what values of lambda that it gives 0 and it gives the roots of that equation are known as eigenvalues. So it's Cayley-Hamilton theorem is clear. Now the problem asked in examination is that we are to verify Cayley-Hamilton theorem for given matrix, or with the help of Cayley-Hamilton theorem we are to find inverse of that matrix if it is non-singular. So we have a problem here. To verify Cayley's theorem for A is equals to, this is a 3 by 3 square matrix, we are to find A inverse and also verify Cayley's theorem. So first we will find characteristic equation for this matrix. Characteristic equation for this matrix is given by determinant A minus lambda is equals to 0. So subtract lambda from diagonal elements and taking determinant into left hand part. Now we will equate it equals to 0. Hence we get characteristic equation as lambda cube minus 6 lambda square plus 1 lambda plus 2 is equals to 0. Now if we want to find its eigenvalue or eigenvector, then we will find its root, and if we are to verify its that Cayley's theorem, it satisfies Cayley theorem, there is no need to find its eigenvalues. Simply what we will do, as Cayley theorem says, every matrix, square matrix, and which is non-singular, satisfies its characteristic equation. It means if this matrix satisfies Cayley's theorem, it should satisfy this equation. Replace lambda with A only. So we get A cube minus 6A square plus 7 lambda plus 2. This is what? Here if we replace lambda with A, so it becomes A cube. A cube is a matrix quantity which is of 3 by 3 order. Again this is lambda square. When we replace with A, we get A square, which is again a matrix quantity of 3 by 3 order. This is again a matrix quantity which is of 3 by 3 order. So matrix addition is possible and matrix subtraction is possible. So to add something, there should be some matrix also. That's why we convert this 2 into some matrix by multiplying this 2 with identity matrix of same order of A. Here these are scalar quantities, that's why result is scalar 0. And here in left hand part these are matrix quantity, that's why left hand part is also a null matrix. This 0 represent a null matrix, not a scalar 0. And the order of this null matrix is also equals to order of this A. So we are to prove this one. So for that, first we calculate the value of A cube, A square, and putting those into left hand part of this expression and obtain right hand part. If successfully we obtain right hand part, it means this matrix satisfies Cayley's theorem. So first we find A square with matrix multiplication. So we all know how to matrix multiply. So first we multiply this first row with first column and we get 5 then this first row with second column we get 0, then first row with third column we get 8. Similarly, we obtain these other values, so a square becomes 5, 0, 8, 2, 4, 5 and 8, 0, 13. Now with the help of a square and a, we calculate a cube. So we multiply a and a square, and hence we get a cube is equals to this one. 21, 0, 34, 12, 8, 30, 23 and 34, 0, 55. Now we'll put a square and a cube in the left hand part of this expression. When we solve this expression, after putting a square, a cube in this expression, when we solve, we look, all terms becomes 0. So we get a null matrix of 3 by 3 order. It means given matrix A satisfies its characteristic equation. So it satisfies Cayley's theorem. Now to find inverse of that matrix, we will multiply this equation with A inverse. Hence we get here A inverse into A cube gives us A square. A inverse A square gives us A into A inverse gives us identity matrix I, and I into A inverse gives us A inverse. And now we equate this equation equals to 0, as 0 into A inverse become 0. So from here we can obtain the value of A inverse, which is given by 2A inverse is equals to, shifting all this term into right hand part, minus I square plus 6A minus 7I. Already we have calculated the value of A square, so we will put here in right hand part the value of A square and identity matrix, and after solving this expression we get 2A inverse is equals to a matrix of 3 by 3 order with row wise minus 6, 0, 4, minus 2, 1, 1, 4, 0, minus 2. And from here we get the value of A inverse is equals to 3, 0, 2, minus 1, half, half, 2, 0, minus 1. So in this way we can obtain the value of A inverse with the help of Cayley's theorem. Thank you.